First speaker this afternoon is Randall, and is from Georgia Tech. And she will talk about mixing of Markov chains, fault lines, and backbone.
Thank you. So first of all, I apologize if anyone is disappointed that there's not a Brazilian woman up here. And so in the program, it says that I'm from São Paulo State, which is my best guess, but he's not here, unfortunately, is the last time I saw Yuval was in Rio. So, caipirinhas are good, Okay, so I'm going to explain to you what fault lines and fat contours are, and all right. All right, well, this was working a second ago. And that's it. Any questions? All right.
You're illustrating slow mixing.
It was working. I think I just set it up too early, unfortunately. Let me try this again. Now it's working fine. Okay, so what's going on? Sorry. I can, yeah. Okay. Okay, so I'm going to look at several models that are motivated by statistical physics. They're computer scientists and combinatorialists too. So independent sets, and thinking about a subset of the vertices, no two sharing an edge. And I'm going to weight it with by lambda to the size of the independent set. So this is a fugacity. And okay, and my interest is sampling from this distribution. Okay, and for all of my models, I'm going to be looking at lattices, not general graphs. So the Metropolis-Glauber dynamics would choose a vertex and try to add or delete it with the correct probabilities so that you converge to the this Gibbs measure. So the details of implementation are not important, but we're all on the same page. I think that we've seen things like this enough. So it's single site dynamics. So what happens intuitively for independent sets, and in all of the models that I look at, I'm going to be considering large lambda, is first of all, notice that you could think of an independent set according to the red points are on the even sublattice and the blue points are on the odd sublattice. Okay, so this is the colored independent set. And what you expect when lambda is large is that you're going to see a lot of mostly blue configurations or mostly red configurations, and you're unlikely to see the types of configurations that I have here that are half and half. Okay, and intuitively the explanation is pretty clear, which is that you have to have far fewer vertices if you're half blue and half red. Okay, so this has significantly less energy, but of course you have to balance this with the entropy, which is that there's actually a lot of configurations that are half red and half blue, and so you have to find some way of calculating this in order to show that when lambda is large enough, you have slow mixing. Okay, and what do I mean by slow mixing? Just to remind you, because several people have, I don't have to do this, I have to get used to that. Okay, so the conductance is a characterization of fast or slow mixing. So, okay, so if your state space looks like this, so you could divide it into two sets so that the flow from S to S complement normalized by the stationary probability of being in S. If this is at least 1 in poly, then you have polynomial mixing. And if it's less than 1 over an exponential, then you have exponentially slow mixing. Okay, so not going to use it more detailed than that. Okay, so going back to this model, if what I had, the intuitive picture I gave you is correct, then in fact you're going to have that this is an exponentially small cut if you go through the balanced independent sets. And the point of this talk is that these proofs tend to be very complicated and very hairy, And hopefully I'll convince you that there are ways to really simplify these proofs in some cases by the end of the talk. Okay, and there are other models that have similar behavior. So we've seen the Ising model a bunch. So pluses are red and minuses are blue, and whenever you have a plus next to a minus, well, you get penalized. So this has much lower weight than something which was predominantly plus or predominantly minus. So again, when lambda is large enough, so I'm thinking about lambda is something like e to the 2 beta in the standard way that the Ising model is written. And again, you're going to find it very hard with single site dynamics to go from something predominantly plus to something predominantly minus. And here's 2 less well-studied models. So independent sets on the triangular lattice. Okay, so you no longer have a bipartite lattice, but of course you have a tripartite lattice here. So there are 3 maximal independent sets, ground sets. And we could see that by looking at this tripartition and 3-coloring the vertices in the independent set. And intuitively, at least, independent sets that are predominantly yellow or predominantly red are going to dominate the stationary distribution. And ones that are mixed like this will have much lower weight, and we don't expect them as much. So it's hard to go from a yellow one to a red configuration. Okay, this one it's called the 8-vertex model. So many of you, maybe without realizing it, have seen the 6-vertex model or the ICE model, which also corresponds to 3 colorings in two-dimensional lattices. So it's called the 8-vertex model. I'm orienting every edge of the lattice so that every vertex has even in degree. Okay, so the 6-vertex model has in degree 2 and out degree 2, so it's Eulerian. And here I'm also allowing sources and sinks. And I'm going to again add a fugacity, so I'm going to weight a configuration by lambda to the number of sources and sinks. Okay, so this is my model. And again, we have a 2-coloring. So it's less obvious at first maybe, but the ground states in this case, the maximal weight states, are when the even sublattice are sources and the odd sublattice are sinks, or vice versa. Okay, so those are the blue and red points. Okay, and so how do we show slow mixing? So we use a takeoff on a piles argument, which is what's used to show that you have multiple Gibbs states in physics. So we've seen that there were commonalities and methods to use to show fast mixing. There's also in slow mixing. So to show that a state space has small conductance, I want you to sort of abstract away definitions, and really what you're trying to show is that your state space, to show, this is so in all of those cases when lambda is large, that your state space can be broken into 3 sets, A, B, and C, so that B has exponentially smaller weight than either of A or B, but to go from A to B, you have to pass through C. That's enough to show that your Markov chain based on local dynamics is, or whatever dynamics that force you to go through C, takes exponential time. And the way that you do this is you define a map from the small set C to, say, the entire state space, so that every time you map something over, you increase by an exponential factor. So you increase this probability when you map by at least C to the n, okay? So if this was an injection, which it typically isn't, but if it was an injection, then you could conclude, if you could map everything from C over, that either this has exponentially large weight or this has exponentially small weight. And well, the total weight here is at most 1 because it's a probability distribution, so you could conclude that this is small, okay? Now, it's not an injection, so you have what I'm calling fan-in. You have several points hitting. But if you could then show that at most a smaller exponential hit the same point, then you can make the same conclusion. Okay, so this is the outline of what we're going to do. And the way that you define this map is you argue that if you're in this middle set somehow, there's got to be a large contour of unhappy edges that want to be happier. And so the standard trick for the Ising model is to take this large contour and flip everything in the interior, and this has larger weight by whatever some lambda to the length of the contour. Okay? And in the context of independent sets, you find a large contour, you take the interior, you shift it over, and that changes its color. Okay? And it also opens up then a bunch of places where you could potentially add vertices. So you add vertices along this side, and you again get something which is exponentially larger, where the amount by which it's larger has to do with the length of the contour size. Okay, and the other two models I mentioned also have contours in like the obvious sense, but as soon as you start playing with them, you see that you actually get stuck, that the flip, the shift, they don't work, and it's hard to imagine what would work. So you have these contours, but okay, in this case, the 8 vertex model, you follow a path of some sort of maybe oriented edges, and what do? I mean, so for this to work, you have to argue that the number of places that this gets happier is proportional to the length of the contour, because you have to identify the contour to invert the math, and that is related to the fan-in. And the same thing here. So this we were stuck on for a long time. So when you have 3 colorings, I'm now using the colorings that were in the Xerox version of our paper, so they're no longer pretty. Okay. If I shift this to the white, I would have to shift to the right to be compatible with white to make some of these conflict edges where I have space to resolve that. And if I do that, then I get conflict with black. Okay, so it's really not obvious what to do for independent sets when you're not bipartite. Okay, so the contours exist, but there's no obvious way to remove them. So what I'll be doing for the talk is presenting the ideas and 2 results. The first one is how to use fault lines to really simplify these proofs of slow mixing. And when it works, it gives very clean proofs. And I'm actually going to almost completely give you the proof. And it also gave, in the independent set case, much better bounds than were known previously, which was just a happy accident. And then I'll show you how to use fat contours to deal with the 2 models where the standard tricks didn't seem to work. Okay, so the second half of this is joint work with Sam Greenberg, my student. Unbelievable. Okay, I'm seeing a little spinny thing going around. So, no, but it will stop. I apologize. Okay, so so the idea of fault lines is, oh, it is there. Let's all stare at, how to hypnotize the whole audience. Okay, so let me just say that in the independent set case, and even in the Ising model case, well, let me just finish this thought. The idea when you partition into A, B, and C, is, or whatever, to make the middle set the balanced guys, okay? So my observation is all you need is something that separates 2 other large sets, and let's define it in a better way so that it's easier to count what's in there. Okay, so I eliminate a lot of things that are just annoying that you don't need to put in the middle set at all, okay? Okay, so what's known about independent sets in 2 dimensions is it's conjectured, as it is in all of these models, that there's a critical point, so that when lambda is smaller, you have fast mixing of the local dynamics, and when it's larger, you have slow mixing. You know, there are bounds that are known for this model that don't get close to the critical point. Many people in the audience are included in this set. And, okay, so this result gets down to the 8.07 that I'll show you. That's the more complicated of these 2. And on the torus, you could actually do even better, and it's just harder for me to draw the pictures, so I'm going to give you the first one almost completely. So, okay. So the way I'm going to define my middle set is in terms of something called fault lines. So if you look at this, maybe this looks balanced. It doesn't have to be, but it's half black and half red are now the colors of my independent set. I have a zigzagging path. It zigzags just because of the nature of independent sets. The densest independent sets are just on the odd sublattice, so it follows that boundary. It's a path from top to bottom that's vacant, and it has width 2, so it's wasteful, or from left to right. A monochromatic bridge is an occupied path from left to right, or from top to bottom, and a monochromatic cross is both of those. So if you have both, they have to be the same color, by the way.
Sorry, is it one defect, so that means that's
You know,
where it steps to the side? Or?
No, okay. So yeah, I'm actually going to ignore this for a second, but basically what it's saying, if you had, imagine each quadrant being as dense as possible, black, red, then I don't exactly have something from the top to the bottom, but I want to think about the one place in the middle where I jump a little bit as a defect. I'll show you later.
But is it basically vertical, or can it?
It could do it. Oh, no, it doesn't have to be vertical at all. It could go like this. It's just a width 2 path from top to bottom that divides into 2 halves. So the defect is a technicality that I'm just going to ask you to ignore because it adds one more symbol to the proof and is really not so important. Okay. I have to not pause and answer questions, apparently. Okay. So the lemma is that, much like we saw this morning in talks, that if there's no fault line, then there is a monochromatic cross. These are tool. Okay. And you need the defect in order to prove that. And if it has an odd cross, and you have another configuration with an even cross, then they're not connected by a single step of the local dynamics, the single site dynamics. Okay, so my partition into the 3 sets A, B, and C now are going to be the things on the left have a black cross. Now notice it could have a black cross and everything else could be red. And so it has many more red points, but I'm still putting it on the black side. The same thing for the right, and the things in the middle are the things that have at least one fault line, which I'm drawing mostly vertically, but they don't have to be. Okay, so my outline, now that I have a set partition that satisfies these criteria, I just have to show that things with faults have low weight. Okay, so I do that by, first I'm going to partition the things that have faults according to where, say, the leftmost or upmost fault occurs, and according to what is the rightmost column of the configuration. So the rightmost column is itself a one-dimensional independent set. Okay, so here's an example of the blue is just representing whatever the independent set is on the right, and it has a fault, which you could see is not monotonically going down. And I need to construct an injection. So it's not going to be an injection from the middle set, but it's going to be from the middle set cross 0, 1 to the n plus L, where n plus 2L is the length of this fault. N plus L turns out to be exactly the maximum number of particles I can add if I were to make a little bit more space. So this will come up in a second. Okay, so I identify the fault line. I push everything to the right of the fault line over by 1. And so I had things that were width 2. Now some places it's width 3 and I could add a particle. Some places become width 1 because I'm looping around, and those I can't, and that's where this n plus L comes from. Okay, and the right-hand column now drops off. And everywhere where I can add a particle, I either do or I don't. Okay, I'd get slightly worse bounds if I just threw in everything, but I'm going to be clever here and say you either put a particle in or not. Okay, that's my map. All right? Okay, so here's my first lemma, which, ignoring the details, this is the line that's important. Okay, so when I do this map, the number of particles that I add, okay, well, I lost all the ones from the right-hand column, but I added as many of the, that vector R is just a 0, 1 vector telling me where to add along that fault line. Okay, so I make the trivial observation that 1 is equal to the size of the whole state space, and this is greater than, well, this was an injection, so the sum of the points that are in the image of the map, and I just write down what I gain by the number of particles that I gain, and I combine terms, and this falls out very easily. Okay, so there's nothing complicated here. I'm not going to go through more details, but okay, so I get the purple lemma is what I just erased. The blue lemma is enumerating lambda to the size of the independent set for the right-hand column. Okay, well, the right-hand column has a nice recursion. It's just the Fibonacci recurrence. Okay, because if I have a particle in the first position, then the next particle has to be at least 2 down. And if I don't, then the next particle could be in the next position. So I have this very familiar recurrence, but with a lambda stuck in because I'm counting whether I added lambda or not, added a particle or not. And if you solve this, you get, notice the golden mean. So if you set lambda equal to 1, this is the solution to the Fibonacci recurrence. So that one's easy. And the green lemma, these are color-coded on purpose. The green one is just counting the number of fault lines of a given length. okay? Well, it's just a self-avoiding walk in the lattice. So this is the only non-trivial result that I ended up looking up to find, is that the number of self-avoiding walks in 2 dimensions is bounded by this to the n. And if you want, just put in 3 to the n, and then this is completely self-contained proof. Okay, so putting the pieces together, the total weight of this middle set containing faults, well, I break it up as to a sum over where the fault is and what the right-hand column was. This is my purple lemma. I rearrange terms. These are my green and blue lemmas. I'm just substituting, okay? And now I combine terms and I get this, okay? And so now the observation is that if each of these quotients is less than 1, then this is exponentially small, okay? So I solve 2 simultaneous equations and I get this, okay? So it says that I have exponentially slow mixing for independent sets as soon as lambda is greater than this. And again, you get a big improvement if you do this on the torus, because you don't even have to worry about the right-hand column falling off. All right, and this also gives incredibly simple proofs in the case of the Ising model. Okay, so this gives slow mixing by using the conductance theorem. Okay, so for the remainder, I'm going to talk about the how you handle these other 2 cases, the independent sets and the 8-vertex model, where it doesn't even seem like you could shift or flip or anything. So again, we're going to start with, instead of the conventional view of looking for balanced sets, we're going to partition according to fault lines in some way, which is going to just simplify the way we look at the picture, but we still need an extra trick here. Okay? All right, so this is to remind you what the problems were. So in the case of the 8-vertex model, which I'll start with, it's going to be convenient to look at this as an edge coloring rather than a vertex coloring. So you get this for free. So any edge, how did I orient it? So it's blue if it points away from an even vertex, the edge, and it's red if it points to an even vertex. It does one or the other because we're orienting them, so it points away or to. Okay, so this configuration here translates to this. And the reason this view is more convenient is that the sources and sinks, which are the points where we want to have lots of when lambda is large, those are monochromatic now. And the Eulerian points that are giving us trouble, those are the bichromatic ones. Okay, so it's just a nice edge coloring. Okay, so again, we want our middle set to be the ones that have a fault line. Okay, so, whoops, I think I skipped a slide, but okay, so a fault line is a path of touching bichromatic points. Touching is just what Rob was talking about before as the star lattice. And am I doing this again? No. Yeah, there we go. It'll stop. Okay, and again, I have this view that what's on the left is a monochromatic cross of blue edges, and what I have on the right is a monochromatic cross of red edges. And again, you have to do a little combinatorics, but these are easy proofs that you can't go from red to blue in one step. Okay, and I want to show that this middle set has exponentially small weight compared to the other 2. Sorry. Did I mention this is a really picture-intensive talk, and my PowerPoint has been having trouble? So
this is Bill Gates' fault.
Everything is. Okay, so what we're going to do, and remember we had this problem that we have these contours, but we don't know what to do with them. So, okay, so to remove a contour, which is what I did by flipping or shifting in the case of independent sets, I'm going to consider a maximal component going through just bichromatic vertices in this star-connected lattice that contain this particular fault line. So rather than looking at a minimal set, which is the d-1 dimensional contour, I'm actually going to look at d-dimensional contours. So in this case, I could have an area considered to be part of the contour, okay? So I look at that whole component, this is sort of combining steps, but I erase that entire contour which contains the fault line. It contains a lot of other junk too, and it separates my remaining graph into pieces. But for those remaining pieces, the boundaries are one color or the other. They're either blue or they're red. So I circled the ones that have a red boundary touching this fat contour, and I'm going to flip those. So I flip everything in that contour, including interiors, I flip as well. And I get this picture, and now I color what I removed completely blue, okay? So when I do that, first of all, notice that if I were, okay, so I get something which has much more energy, in fact, or much more weight in the stationary distribution by lambda to the area of this fat contour, okay? But I actually need a lot of information to reconstruct what's there. And notice that if I told you what the edge colors were in this entire contour, and I gave you the image of the map, then you could reconstruct where you came from. Okay, so to bound the fan in, I have to look at how many of these colorings, how many contours, and how many ways to color it there are. Okay, and this is more complicated because it's not one-dimensional, but I just do a depth first search. So I hit every edge twice. Okay, so I'm not going to get a great bound. Who cares? Okay, so if I do this, I have, I guess, 2 end places to start, because it's either vertical or horizontal. I have end places on the top boundary to start, and then at every step, when I do the step first search, I have 8 neighbors in this star lattice, okay? And it's 64 because my depth first search path is actually going to be twice the number of edges. Okay, I hit every edge twice. So it's not great counting, but nonetheless, the observation is that as long as lambda is greater than that constant, I'm guaranteed to have slow mixing. Okay, so the fat contour is dealt with this case. This I will go through very quickly as I'll show you what happens on the triangular lattice. First of all, we couldn't get it on the grid, so we did it on the torus. It turned out to be a lot easier, as it is on the square lattice as well. Okay, but when things dropped off, we got into some trouble. So now I'm switching to the torus. So the colored triangles are triangles that don't touch a colored vertex at all. So they don't touch any vertex in the independent set. And I look for some fault line which goes through the gray triangles, which are empty. And I take the largest component connected to that. So all the triangles in that connected component. And okay. Yeah, I mean, I'm doing the obvious thing. So there's now 3 sets. So I'm separating blue from both yellow and red. Okay, so I'm looking at all of the things in the middle that have faults. Okay, this is the, my student did these beautiful Moreau-like pictures that I will go through quickly. So the map is now going to be, I have this fault line. I take the maximal component containing it, which is all the white stuff. Now, anything that is connected to this, I want to turn to blue. Because if I turn all of these things to blue, then the entire area that I've removed, I could paint blue, and I get now an independent set that has blue for the entire area. So I gain proportional to the area. So I take the yellow and I shift it and make it blue, and then I take any red component and shift it and make it blue, and now I could add a sea of blue. Okay, and the counting that I did before is going to work. But the problem is that I'm on the torus, and I made a big assumption here that this non-contractible boundary of blue matches the color on the right boundary. So I have a non-contractible fault line, okay, on the torus of empty stuff, and I have some color to my left and I have some color to the right, and if they match, I'm golden, but they might not match, okay? So if they don't match, as here you could see, I can't make this whole sea, even without this red island in there. I can't make it blue because I'm still going to get conflicts along the yellow, so I can't argue I'm going to definitely gain points proportional to the area, okay? If the next non-contractible thing on the other side is also blue, then I'm okay, because then I could shift the yellow and make that blue, all right? And then I can do the trick I did before, all right? And I could keep track of these things because there's only 2 places I have to start. So it's not a connected component anymore, but it's 2 connected components, and this will work. Okay, but that might not happen. Okay, I might have blue and then yellow and then red, but fortunately it's got to stop now. Okay, so, and I know I have to eventually get back to blue because I have a blue bounded component. Okay, so anyway, you work out the details and you get something similar that you get a polynomial times, in this case, 36 to the k, whatever. So as long as lambda is greater than some constant, again, we've shown that, that the size of the set of configurations that contain a fault is exponentially small, and then we could conclude that we have exponentially slow mixing, okay, for some ridiculous constants that we then try to optimize. Okay, so open questions. We'll go fast. Independent sets on the triangular lattice with non-toroidal boundaries. We didn't, work really hard on this, but we didn't get it. This, I think, is a really good question for this crowd, because I think it's somewhat reminiscent of colorings, in fact. Is for the 8-vertex model, what I showed you is that when lambda is large, so lambda is the fugacity on the number of sources and sinks, okay? So when lambda is large enough, we have slow mixing. When lambda is equal to 1, it's just independent. You just hit every edge at least once. And okay, so I never said what the Markov chain is for the 8-vertex model. You choose a square, and you rotate, reverse the edges along the square. Okay, so take a little, and you get back to something which is in the 8-vertex model, because you change every vertex by an even parity thing. Okay, so it turns out we could get lambda close to 1, and we could get lambda exactly 0, because this is a 6-vertex model. And I can't get anything in between. Okay, and these are both coupling proofs, but this is an n log n coupling result, and this is something that we know is more than n log n. So there's something interesting going on here. And finally, extending all of this to higher dimensions I've been planning to do but haven't. So thank you.
Time for one or two questions.
And do you think this will be extendable to 3 and higher dimensions, or is it somehow inherently?
No, it's just complicated talking about surfaces, and I've only looked at problems where there already were results in higher dimensions, so I don't think we're going to get anything stronger than, the topology becomes a problem when you're on the torus, and I think, I worked some of this out with a couple of different people, and you can push it, but we didn't get anything so interesting yet that is going to really simplify the proofs. The simplicity is obvious in 2 dimensions, but a lot of the complications of still remain. So,
but even for the Ising model, Pyrrh's argument, the original bounds in high dimension were very bad and had the wrong monotonicity in dimension, and it took 20 or 30 years before people got bounds. I think they were constant in, the bounds that had the right improvement as you went up in dimension.
okay, so it's probably worth, I think it would, you basically, like for the Ising model, it just lets you reduce to the case where you have large non-contractible contours, which is one of the cases people deal with in this middle set in some sense, and they have to otherwise deal with lots of tiny sets, and I just eliminate having to deal with all of that. So however complicated one of the 3 cases is, will still remain. Yeah.
Okay, let's thank Dana again.